turbines are expensive, so we want to prevent failures by predicting them in advance. So it will help us in reducing the downtime. Also, we may identify faults which will be developed in the systems, and we can arrange parts which will be required for the repair/replacement. So it can help us in manage the inventory and services. Moreover, all the turbines, since they have the same functionality and they are manufactured by similar manufacturers, so different operating conditions determine their efficiency. So we will be able to monitor the whole fleet and simulate feature scenarios and make comparison with the aim to increase the overall efficiency of the fleet. Now the digital twin models, there are basically different digital twin models such as the physical model, data-driven model, and the Kalman filters. So it basically depends on the intended use of the digital twins. So if we want to predict the remaining useful life of the turbine, then we will go with the data-driven model. However, if we don't have the history from the fleet, but we we have some safe thresholds, and we use the degradation model to estimate the remaining life. If we want to simulate feature scenarios and monitor how the fleet behaves, then we will use the physical model. Similarly, the Kalman filter can model the degradation of the turbines as a state and periodically update the state to represent the current state of the turbine. So the objective of the research are to develop a data-driven digital twin model, utilize a machine learning algorithm to predict future failures by detecting vibration anomalies, and improve the reliability and availability of gas turbines by utilizing scale and efficiency methodology, and also to reduce the maintenance cost and downtime. So this is basically a simulation model which was we have developed in MATLAB Simulink. So it basically integrates the physical asset with the virtual asset. So here is the methodology that we have used for the machine learning algorithm. Traditional machine algorithms overlook the simultaneous observations of several outcome variables, and to overcome these limitations, we are using the temporal multimodal multivariate learning algorithm. The TML algorithm handles massive volumes of complicated and diverse data and also captures the interdependencies between variables throughout various time periods and data streams. Large volumes of complicated heterogeneous data are handled by the TML, which captures the interdependencies between the variables. The TML algorithm has a feedback loop which defines itself using real-time data. So here is a flow chart. First we are setting the objectives, then we have the data collection, and then in the DT development. So we are developing the framework and the machine learning algorithm, which is based on the TMML algorithms. And then we integrate the model and the actual simulation data, and then the model is tested. I will show results of this model in the next slide. And then we have self-learning alarms, which are based on KDE. I will explain it later. And then we have scenario analysis, condition monitoring, and then the results are validated. So here are the results. Basically, we used 18 months data and run on the simulator that we made in the Simulink. So we can see that there are some outliers in the last two figures. So basically, those show the imbalance of the rotor. So this was the validation on the TMML algorithm. So by using KDE, we want to track the vibration parameters of the gas turbine over a period of time. The digital twin can predict when the turbine is likely to exceed normal operating limits, and this enables early warning and predictive maintenance actions, minimizing downtime or damage. So basically the conclusion is that we have developed a hybrid techniques in which we have overcome the limitations of the predictive maintenance by using it with a digital twin model. So it becomes a dynamic model. Data is continuously fed to the simulator, and it provides prediction for the upcoming prediction on the remaining useful life or on the fault diagnosis, whichever you have interest. So this is all from our end. If you have any question, next.
Nadeem Hussain from PEL. You were mentioning machine learning model actually, and you are calling it digital twin. So, how much is the success ratio you have calculated about it, that many events, and how accurately your digital twin predicted those?
Actually, I have shown in the chart where we had a rotor imbalance issue. So we took the last 18 months data and fed it to the simulator, and it provided the same results. But however, if you have case studies of other turbines and you provide it to this algorithm, its efficiency increases. So the more you train it, the more better it provides the results. So this is basically, the research is in infancy stage, and we will improve it, inshallah, in the future.
Thank you.
Bilal, can you please explain how you are calculating the remaining useful life of the turbine using the vibration data?
Basically, that is the data-driven model. I have worked on the physical model in which we took the parameters, and it provides indication on the vibration, which were charts which were on the outliers. So if you want to use the remaining useful life, you have to use the data-driven model. So that was a separate research idea. Means that's different from what we done. It is one of the areas of the digital twins, but we have worked on the physical model, not on the data-driven model.
Okay, exactly what data you are using for the remaining life?
Actually, we used manually data and provided in Excel sheet all the turbine data. It was not live streaming because we don't have integration of the hardware with the MATLAB simulating. If you have using right now, we are purchasing the SAP HS module. So in that we have the meters data. So from that you can transfer the data to the simulator. But at present, with the system that we have at our plant, Dakni, we cannot transfer the live data to the MATLAB simulator.
Right, thank you.
Okay, thank you. Nice
Thank you, sir.